Good evening to all of you from India. I am Shomok Bhattacharya from IIT BHU Varanasi. And the students over here, mostly the research scholars, are going to form a Sigma Xi student chapter. And Sigma Xi, as you know, is a non-profit scientific research honor society for scientists and engineers at the international level. Given this, for the January session, we have requested Professor Ajoy Ghatak to deliver a lecture on his pioneering work on optics. Now, let me quickly introduce our distinguished speaker, who is currently the president of the National Academy of Sciences and also the honorary professor at the Center for Optics and Photonics at IIT Delhi. He received his BSc from Agra College, MSc from Delhi University, and PhD from Cornell University. After a research associateship at Brookhaven National Laboratory, he joined IIT Delhi in 1966. Professor Ghatak has research interests in fiber optics and quantum mechanics. He is the recipient of many prestigious awards, including the CSIR Bhatnagar Award, SPIE Educator Award, Esther Hoffman Beller Medal, OSI Amita De Award, ICO Galileo Award, and the 2020 Sang Soo Lee Award for his seminal role in the development of fiber optics and guided wave photonics, and for pioneering optics education in India. Most recently, he received the 2021 Shastra G. N. Ramachandran Award for excellence in physics. He will explain in detail about his work in this talk. So thank you very much, sir, for accepting our invitation. So I don't want to waste any further time of yours. So please, sir.
Thank you. Can you hear me?
Yes.
And okay. And can you see my slide?
Yes, we can see. We can see. Yes.
Thank you very much. I will just make one small correction to your introduction. Thank you for your very kind introduction that I am no more the president of the National Academy of Sciences, India. That ended on 31st of December, 2022. So, but I am very closely associated with that academy, and I am very proud to be associated with that academy, which is the oldest science academy in India, founded by Professor Meghnad Saha in 1930. And we are trying to continue his vision of science and society. And so that's about it. So I'm going to give a very elementary talk, primarily meant for students, but I see very senior. So this is going to be an elementary talk, primarily meant for young students. We will start with a brief history of light, and then evolution of quantum theory and various theories associated with it. As you all know, it was not Isaac Newton, but René Descartes in 1637, he derived Snell's law, and his derivation assumed corpuscular model of light. But people usually attribute Isaac Newton with the corpuscular model of light because Newton wrote that famous book on optics, and the book became extremely famous. And in that book, he wrote that are not the rays of light very small bodies emitted from shining substances. And using conservation laws of momentum, he could derive the Snell's law. So around the very fact, the rectilinear propagation of light demands very sharp shadows, and the very fact that you can read a book in the shadow is because of the scattering of light and not because of diffraction. So the scattering of light by air molecules. In fact, if you are on the surface of the moon, then the shadows are very sharp, very dark, and the sky is completely dark. That is because there is almost complete absence of atmosphere on the surface of the moon. And so therefore, experiments like this validated the Newton's corpuscular theory. At the same time, Christian Huygens had put forward the wave theory of light. I don't have to tell you about it. He wrote the famous book. But people believed in Newton much more than Newton believed in himself. And so no one, people thought that Huygens was wrong, and the corpuscular model of light became established, and it has been usually attributed to Isaac Newton. So what is a wave? As we all know, that if you hold a string and make it move up and down and execute simple harmonic motion of one end, it propagates a disturbance. So this is an X polarized wave because the displacement of the string is in the X direction. And this equation describes a wave, as you all know. X of zt is equal to the wave propagating in the Z direction and with a velocity equal to omega by k. And that velocity can be determined from the fact that if I take k outside, then it becomes z minus vt, where v is equal to omega by k. So if at t equal to 0, it is cos kz, then at a slightly later, the displacement, it gets shifted by a distance v delta t. So in a time delta t, the displacement shifts by v delta t. Therefore, v, which is defined to be equal to omega by k, represents the velocity of the wave. So if I find a solution like this for a particular system, then I can predict the existence of a wave. And of course, k is equal to 2 pi by lambda. Similarly, you can have if you oscillate the string in the y direction, then you have a y polarized wave, and a y polarized wave is defined by this particular equation. And you can have a circularly polarized wave also, in which you rotate the string in the clockwise direction, generating what is known as a right circularly polarized wave or a left circularly polarized wave. In the case of an electromagnetic wave, it is the electric field at a particular point, the direction of which rotates in the clockwise or in the anti-clockwise direction of the circumference of a circle. So if you have 2 point sources vibrating in phase on the surface of water, this is an animation on a ripple tank, then the vibrations the displacement produced by each of the wave interferes, and you have an interference pattern. And this is the actual interference pattern produced from 2 point sources vibrating in phase in a ripple tank. This photograph is from the PSSC book, very famous book on physics. So this is a the interference phenomenon, as you all know, is a characteristic of the wave. But it was only in 1801 that Thomas Young carried out this very beautiful experiment in which he used 2 pinholes, allowed monochromatic light. He passed the sunlight through a filter and allowed them to interfere and produce interference fringes on a screen. And by measuring the distance between 2 dark image lines, you can calculate the wavelength, which is beta is the fringe width, d is the small distance between the 2 pinholes, and capital D is the distance between the 2 screens. So he could calculate the wavelength, and he could find out that the wavelength associated with this is about half of a micron. This is considered to be one of the most beautiful experiments in science. What I want to mention to students is that in Thomas Young's original experiment is not a double slit experiment, but a double hole experiment. And you get almost straight line interference fringes. Actually, the interference fringes are not strictly straight line, they are hyperbolic in nature. But almost if the distances are small, the wavelength is small, then you get almost straight line fringes, which was first observed by Thomas Young and which established the wave theory of light. Because if it was indeed particles, as was beautifully described by Feynman in his famous lectures, this particular diagram is adapted from Feynman lectures, then the bullets coming out of the gun will either pass through hole number 1 or hole number 2. So if hole number 2 is closed, you get an intensity pattern like this. If hole number 1 is open, then you get hole number 2 is open. And when both holes are open, then the bullets either pass through hole number 1 or hole number 2, and you get some of the intensities. So this is what you should have expected on the basis of a simple particle model of light. On the other hand, if light was indeed a wave, then the waves interfere. The displacements, the superposition principle, which is a consequence of linearity of Maxwell's equations, The superposition principle tells us the displacement produced by one wave is by the two waves is this algebraic sum of the two displacement, or the vector sum of the two displacement. And if they are out of phase, then you have dark points. And this can only happen. That is, here, if either of the hole is open, then the intensities are large, but both holes are open, it is dark. So light plus light can produce darkness. So this is a manifestation of the wave nature of light. And this is actually a quotation by Max Born, who said that Thomas Young's experiment said that light plus light can produce darkness, which is possible only if light is a wave phenomenon. So Thomas Young's experiment established beyond doubt that light was indeed a wave, and then there were a large number of diffraction and polarization experiments performed. And soon it was established around the beginning of the 19th century by many experiments on diffraction that light was indeed a wave. Thomas Young is usually referred to as the last man who knew everything. Thomas Young, he was a doctor, the anonymous polymath. There is a book by Andrew Robinson, the anonymous polymath, who proved Newton wrong, explained how we see, cured the sick, decided of stone, among other feats of genius. And people say that the last two people who knew the entire physics, people say it's Richard Feynman and Lev Landau, and after that no one knows the entire physics. And Thomas Young is the person who knew everything of science. So the main question, as you all know, that in the beginning of the 19th century was light was a wave, but how could the wave propagate through vacuum? And that was the main question, and the concept of ether came in. And now we know that the ether does not exist, so I will not go into the details. But at around the same period of time, the laws of electricity and magnetism were getting established. Faraday discovered that if you have a magnet which you move up and down, and it generates an electric field, and Maxwell put that in the form of an equation, which is one of the laws of electromagnetism, that a changing magnetic field produces a changing electric field. And similarly, Ampere had discovered that a current produces a magnetic field, and that also law Maxwell put in the form of an equation. For example, curl of H is equal to J. But then he did something remarkable, as I'm sure all of you knew. He introduced the concept of the displacement current. He said that not only a current produces a magnetic field, as was shown in the previous slide, but an oscillating electric field also produces a magnetic field, like between the two plates of a condenser. When there is vacuum there's a changing electric field, and that produces a magnetic field. And this introduction of the displacement current revolutionized physics. And for example, in free space, the Faraday's law, if I write down, and if I substitute a wave-like solution for that, then you will get the corresponding magnetic field is given by this. So what I've done here is I have assumed a wave-like solution for the electric field, taken the curl of that equation, and then integrated with respect to time and obtained the expression for magnetic field. So associated with an electric field, there is a magnetic field. And then if you use these two equations and substitute in this, this is the displacement current. This is as Maxwell modified the Ampere's law. If you substitute that, then it also satisfies that. And you can calculate omega by k. If you substitute this and this in this equation, then you will find that omega by k will be equal to 1 over under root of mu 0 epsilon 0, where mu 0 is the magnetic permittivity of free space, epsilon 0 is the dielectric permittivity of free space. And if you substitute their values, then you get a value equal to this. So what Maxwell did, then, as I'm sure all of you know, he said that he introduced the concept of displacement current and said that wave-like solutions are possible of the laws of electricity and magnetism. And so therefore he predicted the existence of electromagnetic waves, the velocity of which will be about, he predicted, 300 million meters per second. And this was around 1860 or so. At that time, Fizeau has measured the velocity of light, and it was indeed in the vicinity of 300 million meters per second. And Maxwell said that these two numbers cannot be accidentally equal. And so therefore, with faith and rationality of nature, Maxwell made that great prediction that light must be an electromagnetic wave. So for the students, I will just repeat what I have just now said. He said that a wave-like equation for the electric and magnetic field are solutions of Maxwell's equations. And from the Maxwell's equations, which are experimental laws, he could calculate omega by k, and therefore the velocity of the electromagnetic waves. And he calculated, not measured, he calculated the velocity of the electromagnetic waves to be 300 million meters per second, which was the value of measured by Fizeau for the velocity of light in air. And so therefore he said that these two numbers cannot be accidentally equal. And so therefore light must be an electromagnetic wave. This was a revolutionary contribution made by Maxwell around 1864, that light itself is an electromagnetic wave. Associated with a light is an oscillating electric field. The oscillating electric field produces an oscillating magnetic field, and oscillating magnetic field produces an oscillating electric field. That is how it propagates in free space. The concept of fields, today we take it for granted, but it was first introduced by Michael Faraday, the concept of fields. And I think that is a great introduction, the great contribution to physics as such. So as Feynman says that, and God said, let there be Maxwell's equation, and there was light. Once again, Maxwell's equations cannot be derived. They are experimental laws. They describe the various experiments, and the addition of the displacement current was done by Maxwell around 1860. So as we know that the entire electromagnetic spectrum ranges from gamma rays to radio waves. They are all electromagnetic waves. All wavelengths rigorously travel in free space with an identical velocity of 299792458 meters per second. The X-rays have a little higher frequency than the ultraviolet, and then the visible, infrared, microwave, radio waves, and the waves that you receive on your cell phone, in which the visible portion occupies only a tiny portion of the electromagnetic spectrum. Electromagnetic waves generated by electric circuits was first established by Heinrich Hertz in 1887. He used an antenna which produced electromagnetic waves and an aluminum screen, and then generated a stationary waves from which he could calculate the wavelength. The wavelength, of course, was much larger. In fact, Jagadish Chandra Bose also made some revolutionary contribution using the electromagnetic waves around that period of time. And this is now very well documented by the IEEE journals, the contribution made by Jagadish Chandra Bose, who was an Indian physicist in Kolkata. So he calculated the wavelength, he knew the frequency, and he found that the velocity of these electromagnetic waves generated from electric circuits was the same as the velocity of light. So it was Heinrich Hertz's experiment in 1887, around that time, that electromagnetic wave theory could be established. Using Maxwell's equations, one can solve almost in the entire physics, the origin of refractive index, the reflection and refraction of light from dielectrics to metals, everything could be understood. So finally, Max Planck had said Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. And then in 1894, when Maxwell's theory could explain everything, Lord Kelvin had said that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. And then came Einstein. And then in 1902, Philip Leonard, who was I'm sure all of you know that he was very anti-Jewish and he didn't like Einstein and everything. But that is another story, that is another topic of discussion. But whatever it is, he observed that he observed the first photoelectron, the kinetic energy of the emitted photoelectrons was independent of the incident intensity of the incident light, and that the energy of the emitted electron increased when the frequency of the incident light was increased. So this was observed by Philip Leonard in 1902. And when he read that paper, he received the 1905 Nobel Prize in Physics for his work on cathode rays. And there is a very beautiful documentary on Einstein that has come out by National Geographic, and in which he said that Einstein got very excited when he read that paper. And in the year 1905, Einstein, sitting in a Swiss patent office in complete isolation, published 5 outstanding papers that changed the face of physics. These 5 papers are often referred to as the Annus Mirabilis papers. Annus Mirabilis are Latin words meaning year of miracles. So we discovered, for example, the equation of V equal to mc square, and special theory of relativity, theory of Brownian motion, and everything. But there is a very beautiful book by John Stachel, on edited book, Einstein's Miraculous Year, 1905, 5 papers that changed the face of physics. And in the second paper, in his Year of Miracles, Einstein wrote, quantize the light, wrote radiation energy consists of indivisible quanta of energy, whose energy is given by h nu. And so the concept of the light quantum was introduced not by Max Planck, but by Einstein. What Max Planck did was that he quantized the energy levels of the oscillators. Many people, even some books, write it wrongly. So the quantization of light was first introduced by Einstein in 1905, and in a later paper, he said that the momentum associated with the photon, this light quantum was named as this light quantum was introduced in 1905, and the momentum was introduced in a slightly later paper, and the photon word was introduced by Lewis in 1926. So Einstein's light quantum is now known as the photon. So this was a revolutionary concept, as you all know, and eventually led to the development of quantum theory. So he explained photoelectric effect, he derived this equation, which is known as Einstein equation. Many books write that using he could derive the light quantum to explain photoelectric effect. That is not correct. He calculated the entropy of a gas inside a light, in the electromagnetic radiation inside a cavity, compared with that of a gas. From that, he got the concept of the quantum. And once he got the concept of the quantum, light quantum, he explained the photoelectric effect, and he wrote down this famous equation, which is h nu is the energy of the light quantum, and B is a constant depending on the metal surface that you have. And this was verified in 1914 by Robert Millikan in a series of very beautiful experiments. And he verified this Einstein equation for various metals with a tremendous degree of accuracy. And both Einstein, it took a long time for Einstein to receive the Nobel Prize in 1922. So the story goes that in 1921, there was so much of a fight in the Nobel Committee that no one was given the Nobel Prize. And so you think that the politics is in India, the politics is everywhere. There's a very beautiful book by Friedman on politics of excellence, in which they say that many people who deserve the Nobel Prize do not get the Nobel Prize. And but eventually he got the Nobel Prize. By then, his general theory of relativity was very well established, but they didn't want to give him for the theory of relativity. There was a change in the committee. It's a beautiful story. Everyone should read that, the Friedman's book, which tells us the story that how Albert Einstein was denied the Nobel Prize when his general theory of relativity was put forward in 1916, verified experimentally in 1919 by Arthur Eddington. Whatever it is, I leave that story for you to read separately. Then Robert Millikan also received the 1923 Nobel Prize in Physics. And So although he received the Nobel Prize, but you see, he got the Nobel Prize for this equation. The light quantum, the concept of the photon was still not established. It was only when Arthur Compton in 1923 carried out his beautiful scattering experiments in the United States that that a light quantum hits an electron, and the scattered photon has a smaller frequency, and he calculated the wavelength of or frequency of the scattered photon, and using simple dynamics and simple kinematics, using Einstein's light quantum and the momentum associated with the photon, and which matched very beautifully with his experiments. So it was the 1923 experiment of Arthur Compton which established that light indeed had a quantum-like structure, as was predicted by Albert Einstein in 1905, and Arthur Compton received the 1927 Nobel Prize for his famous scattering experiment. This is the wave-particle duality, which led to quantum theory. So as you all know, J.J. Thomson discovered the electron, and now we know the mass of the electron to 10 decimal places to a tremendous degree of accuracy, the charge of the electron to a tremendous degree of accuracy, and you can bend it by electric and magnetic fields. So on the back of your mind, you feel that the electron or the proton is a tiny particle. So then Louis de Broglie in 1924 in his doctoral thesis said that P is equal to h nu by c is equal to h by lambda is the momentum of a photon. So this is also valid for electrons. He predicted that. He predicted that in his doctoral thesis. And one of the arguments that he put forward was, by that time, 1913, Bohr had put forward the theory of the hydrogen atom, in which he quantized the angular momentum. He quantized the angular momentum to get the Balmer series. That is another story. He quantized the angular momentum. How could he quantize the angular momentum? He quantized the angular momentum so that he could get the Balmer series. And it's a very beautiful history. And Louis de Broglie said that this equation implies, the quantization of the angular momentum implies that 2 pi r is equal to nh by v is equal to nh by p, so that each stationary orbit of Bohr atom has integral number of wavelengths, something like a stationary state. And therefore, he justified his formula lambda is equal to h by p. So Niels Bohr had actually come to Delhi University, and I was at that time secretary of the Physics Society. So here is Niels Bohr, and for those who know Professor Olak, he was a physics professor, Professor R.P. Mitra, Professor D.S. Kothari is somewhere here. But we had the great privilege, and we just looked at him. I still remember the talk that he gave at Delhi University. So I'm a prehistoric man. You see, I have seen Niels Bohr. And I had picked him up from Maiden's hotels in Delhi. And it was just a great experience. So Niels Bohr received the 1922 Nobel Prize, and Louis de Broglie received the 1929 Nobel Prize in Physics for his discovery of wave nature of electrons before the experiments were performed. So that is the most important thing, that de Broglie, the correct pronunciation, de Broglie. I do not know that, but in India we call him as de Broglie. So in 1926, after the doctoral dissertation of de Broglie, the wave nature of electrons was experimentally established by Davison in Germany and by G.P. Thomson. Davison in Germany in the United States, and G.P. Thomson in England. And this is the diffraction pattern produced by aluminum foil, produced by X-rays, and produced by electrons. So you see the similarity in the interference pattern, the diffraction pattern. So if the photon is a wave, if the light is a wave, then the electron is also a wave. If the light is a particle, then the electron is also a particle. They are similar. That is the most beautiful aspect of this experiment. So therefore, the wave-like property of the electron was predicted by Louis de Broglie, but confirmed by experiments in 1926. by these three gentlemen. Of course, Davison and Thomson got the Nobel Prize, German missed out. So Davison and Thomson shared the 1937. Why did German missed out? I don't know. And there is again a story behind that, whatever that is. So now comes the main lecture. So is the electron or a proton a wave or a particle? Some books write it's sometimes a wave, sometimes a particle. That is not right. It is a wave and a particle. That is also not right. The correct answer, and that is Richard Feynman writes that they are neither waves nor particles. So I really not answered the question that this is the electron or a wave or a proton is a wave or a particle. Richard Feynman writes they are neither waves nor particles. Then what are those? Then what are, I have not really answered the question. They are described by the wave function psi, which is the solution of the Schrodinger equation. So what is an electron? Free electron, for example. It is described by this symbol psi, which is complex in nature, which is the solution of the Schrodinger equation. And then Feynman very beautifully writes that where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. That is the most beautiful sentence. And I quote Feynman because if I had said that, probably some of the students will not believe me. So we cannot derive Schrodinger equation. You cannot derive quantum mechanics from classical mechanics. Of course not. So Feynman very boldly writes, where did we get that equation from? Nowhere. It is not possible to derive it from anything you know. It came out of the mind of Schrodinger. My God, that is so beautiful. So it is so beautiful that people have tattooed them on their back. And so let me give you a heuristic, non-rigorous derivation of the Schrodinger equation. So I have psi of xt is equal to so much. So I use the de Broglie relation, which is p by h by lambda, divide and multiply by 2 pi, you get h cross k. So k is equal to p by h cross. So h cross is equal to h by 2 pi. We also have the Einstein relation, which is E is equal to h nu, h cross omega. And then I substitute for k and omega here. So thus we may write that if I have to have a wave-like equation. Wave-like, this is what Debye had told Schrodinger. Debye had told Schrodinger there must be a wave-like equation for the electron. So he didn't, this is not his derivation. He derived he obtained a series of logical arguments. You cannot derive that. So then what I do is that for a free particle, E is equal to p square by 2m. So I substitute it here. And then I differentiate with respect to time. I get this. And I differentiate twice with respect to x, I get this. So the right hand sides are equal. And I get very heuristically, non-rigorous. This is not a derivation of the Schrodinger. Some books give this derivation, including my own book. So this is just a derivation, but we have to keep in mind that there is no rigorous derivation of the Schrodinger equation. So this is one-dimensional time-dependent Schrodinger equation for a free particle. Once I have written that out, don't ask me how I have got it. I got it, and now I take that as a Bible and solve this equation and see the results of the equation. So what is my electron? Electron is described by the wave function psi, which is the solution of the Schrodinger equation. And for a free particle in one dimension, I have just given a heuristic derivation of the Schrodinger equation. So let me solve it. So I forget how I have got it. Every book has a different way of getting to the Schrodinger equation. If you read Feynman's book, it is different. If you read Dirac's book, it is different. If you read Schiff's book, it is different. If you read White's book, it is different. So I solve it. Now I take this as a mathematical exercise. I solve it. I solve this using the method of separation of variables. The variables separate out, and therefore I get this as the solution of this equation. This as the separable solution of this equation, where p is now a constant, is a number, whose values can be from minus infinity to plus infinity, and therefore the most general solution is the sum of the sum of all those solutions. So this describes what is known as a one-dimensional wave packet, which is a rigorously correct solution of the one-dimensional time-dependent Schrödinger equation for a free particle. And then in 1926, Max Born used the Schrödinger equation to deduce that mod psi squared dx is the probability of finding the electron between x and x plus dx. And then using a series of arguments, one could show that this is the momentum distribution. A of px mod square is the momentum distribution, probability of finding the x component of the momentum between p and p plus dp. I still have 18. So now consider, I want to study the solution. Consider a function f of t. Fourier transform is given by this. I'm sure all of you knew that. And you have a inverse Fourier transform. If I take an optical pulse, just classical physics, no quantum physics. I take an optical pulse, Gaussian optical pulse of duration tau, and take its Fourier transform, then this is the frequency spectrum. So a pulse of duration tau has a frequency spread of the order of 1 by tau. So you have this, a pulse at say 20 femtosecond pulse. If I take the Fourier transform, then the frequency spread, as you all know, is of the order of, this is the uncertainty relation, delta omega delta t. This is a purely classical result. There is no quantum mechanics here. This is a purely Fourier transform result. And this appears because of Fourier transform. So Fourier transform of a time-dependent function gives the frequency spectrum. And if the duration of the pulse is delta t, then its frequency spread. That is, it is superposed with frequencies, with different frequencies, is of the order of delta omega delta t is 1. So now you do the same thing for the one-dimensional wave packet. So you write down at t equal to 0. So you put this term goes out. So this is the Fourier transform relationship. And the inverse Fourier transform becomes this. So if I know psi of x comma 0, then I can find out the momentum distribution. And if I know the momentum distribution, you can find out the wave function at a later time. So let me assume a Gaussian wave packet. Gaussian wave packet, a particle described by this, an electron or a proton or a neutron or even an alpha particle, described by a wave function which is localized within the distance of sigma 0. So this wave function tells us that the particle is localized within a distance sigma 0. This is the probability distribution function. This is the probability distribution function. And if I take the Fourier transform, then I will find that the delta p is of the order of h cross by sigma naught. So I get the uncertainty principle that is contained in the solution of the Schrödinger equation. So a major part of books on relativistic quantum mechanics is just the solution of the Schrödinger equation. And the uncertainty principle is a consequence of the Schrödinger equation. Now I do this very beautiful experiment. I do the single slit experiment. So I allow a beam of the electron to pass through, a wave to pass through. And as is given in almost all books on optics, that you consider the diffraction of light or a wave by a slit, and you get the Fraunhofer diffraction pattern equal to sine square beta by beta square, where beta is equal to pi b. B is the width of the slit, sine theta is the angle of diffraction, and divided by lambda. This is the standard diffraction pattern of the in wave theory. Now I do the corresponding quantum mechanics. I say that electron is described by a wave function, which is 1 over root b. That is, I make the electron pass through this slit. So therefore, the probability of it finding outside this region is 0. It has passed through the slit. I know that it has passed through the slit. So I describe that with this wave function. And then as soon as I describe this, I can calculate the corresponding momentum distribution function. And I get the same expression for the probability momentum distribution as we had obtained from classical wave theory. So classical wave theory tells us this is my intensity, distribution. Quantum theory, solution of the Schrödinger equation, gives us that the probability that the x component of the momentum lies between px and px plus dpx is given by this, where beta is the same quantity. So How do we understand this? When I pass the electron through a slit of width b, the slit imparts a momentum. And the probability of the momentum lying between px and px plus dpx is the same as the intensity distribution.
Is there any problem in voice of Professor Ghatak?
Yeah, you can't hear anything. It cut out.
There's a problem that electrons may have vetoed photons, meaning the electrons may have gone away.
Yeah.
So Somak, it's your department.
Okay, so maybe I can give him a call.
Yes.
Yeah, please.
Can you see me?
Yeah, it's all right. Yeah.
Please, please share your screen.
I'm sorry, I had forgotten to put the charger there, so that got. I'm sorry. Just let me share the screen once again. Can you see the screen?
Yes, please, but turn it on presenter view.
Huh?
Yeah. All okay.
Can you hear me?
Presenter view again, please.
Oh my God.
Yeah, we can hear you.
I can hear you. Just put it on presenter view.
Okay. So I'll just hurriedly finish now. Sorry, I'm sorry. So I now do the double slit experiment. I do the double slit experiment and I get this intensity distribution from classical wave theory, and then I do the corresponding solution of the Schrodinger equation, and then I calculate the probability distribution, and I get the same probability distribution test. So therefore, quantum mechanics is a probabilistic theory. Classical mechanics is a deterministic theory. So therefore the question is whether an electron or proton, this thing is a wave or a particle. It is neither a wave nor a particle, and electron passes through both the holes simultaneously. If the electron was a particle, then it will either pass through hole number 1 or hole number 2. But we see that they pass through both the holes, it interferes with itself and produces this intensity distribution. And this is the very beautiful single electron interference experiment done by Tonomura and many others, and which establishes that if you do with 10 electrons, you get 10 spots, but which if you do with millions of electrons, you will get an intensity pattern as predicted by the wave theory. This is considered as the most beautiful experiment in science. Let me skip this. So the most fundamental theory now available is probabilistic in form and not deterministic. So I have an incident wave packet. Let us suppose an electron or a proton sees a potential well, and in normal textbooks you will have a reflected wave packet and a transmitted wave packet. So there is a certain probability of reflection, certain probability of transmission. So therefore, an incident particle, which is described by this wave function, when it interacts with the potential barrier, it is here as well as there. So this is the basic concept of quantum mechanics, that an electron, after reflection, it is here as well as there. When you make a measurement, then it is either here or there. It collapses. This is the collapse of the wave function. So similarly, if you do a single photon source with a beam splitter, then you will normally say 50% of them will come here, 50% of them will come here. That is a wrong answer, unless you make a measurement. The photon is here as well as here. The photon is described by a state which is here as well as here. and you can superpose them to produce an interference pattern. So let me do a simple experiment with double refraction. So this is a calcite crystal. This photograph was provided to me by Vengu. So when an unpolarized light beam is incident normally on a calcite crystal, it usually splits up into two linearly polarized beams. So you have here, let us suppose a 45-degree polarized beam. Then classical theory tells us that half the intensity will come here, half the intensity will come here. It is X polarized and Y polarized. But let us suppose I have a 45-degree polarized photon here. Then if you do not make a measurement, then it is in both the beams, it is in a superposed state. So this concept of superposition is extremely important in quantum mechanics. So this device is an XY device. So no matter what the incident polarization is, it splits. What happened?
You're fine. Please continue.
So you can change the orientation of the calcite crystal and produce a UV device. So you can have an XY device, you can have an UV device, you can have a sigma eta device, so that if an electron, if a photon falls in, then it splits up into two polarized states, which is sigma and eta. Now I consider this experiment calcium, which emits two photons in opposite directions. And experiments tell us that if this is X polarized, this photon is X polarized, then this photon is Y polarized. Before the measurement is made, I can only tell that the state of polarizations are orthogonal to each other. As soon as you make a measurement, it collapses to being X polarized. Then I don't need this detector. Then I don't need this device. And it will fall, it will collapse to a Y polarized state. So these two photons are said to be entangled. According to quantum theory, the polarization of the photon traveling to the left or to the right is not known before one of them is measured. Similarly, you can do this, you can think of the Sturger-Lake experiment, that electron it can be thought of as a magnet. It has a magnetic moment. And this magnet classically can be oriented in any possible direction. But if you make a measurement, then it is either the Z up state or the Z down state. So this is a Z up, Z down polarizer. On the other hand, if I take a Z up state, that is all magnets pointing in the upward direction, and pass through a Sturger-Lake apparatus in the X direction, then it will split into X up and X down, because this is a superposed state. So assume two spin half particles in the singlet state. Then it is up down minus down up. So if one of them is up, then the other is down. But if you measure this as up state, then you don't have to measure the second particle. They are entangled. So this two spin half particles in the singlet state is an entangled pair. So similarly here, once the left side is X polarized, the right side collapses to being Y polarized. So if the photon going to the left is passed through an XY device and it is found to be X polarized, then the photon going to the right collapses to a state which its polarization state is Y polarized. And similarly, if you have a UV device and it is found to be U polarized, then the other will be V polarized. These are the famous Alice and Bob experiments. Whatever happened to one particle would thus immediately affect the other particle wherever in the universe it may be. Einstein called this spooky action at a distance. And in German, Einstein said this. So in 1935, EPR wrote in a paper, if quantum theory was correct, then two particles which are millions of kilometers apart can be entangled in the sense that by determining a property of one of the particles, the property of the second particle can be instantaneously changed. And special theory of relativity forbids the transmission of any signal faster than the speed of light. This came to be known as the famous EPR paradox. About 30 years later, experiment confirmed the predictions of quantum mechanics, namely Einstein's impossible proposition was in fact correct. Instantaneous changes in widely separated systems did occur. So EPR argued that if without in any way disturbing a system, we can predict with certainty, that is probability equal to unity, the value of a physical quantity, then the second particle must have possessed the measured property before the measurement was carried out. So therefore, he said the existence of hidden variables, that two photons are going here, there is something written on that if you pass through an UV device, it will be V polarized. If you pass through an XY polarized device, it will be Y polarized. If you pass through a sigma eta device, it is eta polarized. Then the other one is orthogonal to this. So if you pass through an XY device, it is X polarized photon. So therefore, there are 8 possible things that can happen. That is, you can label, this is the basis of hidden variables. I'll take 5 more minutes. I'm sorry, I should have rehearsed this once, so I'm crossing my time. So there are 8 possible things. So probability that the left photon is passed through the XY device and is measured as X polarized, and the right side photon is passed through an UV device and measured to be U polarized, comes from only these two pair, which is N3 plus N4 by N. N is the total number of this. Similarly, probability that the left photon is passed through an XY device and is measured to be X polarized, and right photon is passed through a sigma eta device and measured to be sigma polarized. This happens only in 2 cases like this, and that is N2 plus N4 by N. And similarly this. So you get P of X comma sigma so much, P of sigma comma U so much. So you add them up, you get this. And then P of X comma U is so much. So this is greater than this. So this is a simple form of what is known as Bell's inequality. Bell's inequality. So this is simple form of Bell's inequality, which was put forward by John Stuart Bell in 1964. So according to quantum theory, now this slide is very important, that let us suppose this is X polarized. I pass through an XY device, it is X polarized. Then the right photon, according to quantum theory, will be Y polarized, so that the probability that it is U polarized will be given by the Malus's law. And that will be the probability will be cos square pi by 2 plus theta, and that is sine square theta. So you can do this very easily. I'm skipping the details. Sine square theta comes out to be sine square phi plus sine square phi minus theta. If we assume theta is equal to 2 phi, the above inequality will imply 3 by 4 less than 2. So this is an impossibility. So therefore, Bell's inequality and quantum theory are inconsistent. Thus, quantum theory and Bell's inequality are not compatible, which implies that either quantum theory is right or theory based on hidden variables, but not both. And there are a large number of experiments which have proved that the results predicted by quantum theory are correct and hidden variables do not exist. So this is an apparatus created by Alan Aspect for performing a Bell test. A source emits a pair of entangled photons, nu1 and nu2 of different colors, and are analyzed by those XY devices and UV devices, proving that the Bell's inequality is not valid. So Aspect I don't know whether you call it aspect or ape. The linear polarization correlation of pairs of photons emitted in a radiative cascade of calcium has been measured. The new experimental scheme using two-channel polarizer is a straightforward transposition of the EPR Gedanken experiment. The present results, in excellent agreement with quantum mechanical predictions, lead to the greatest violation of Bell's inequalities ever achieved. So Bell's theorem represents, to quote Anton Zeilinger, who also got the Nobel Prize, as one of the most profound discoveries since Copernicus. Bell delivered a death blow to the local realistic picture of the world. Many experiments have demonstrated that the predictions of quantum mechanics for entangled particles are correct, are fully correct, and the world is really as crazy as predicted by quantum mechanics. This is from the book The Dance of the Photons, which Vengu you had gifted to me. So electrons do not behave just like particles. They do not behave like waves. That is what Richard Feynman said in his famous messenger lecture in Cornell. Electrons in orbit are not somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one simplification at least. Electrons behave exactly the same way as photons. They are both screwy in, but in exactly the same way. And I think I can safely say that nobody understands quantum mechanics. So that is what Richard Feynman has said in his famous messenger lectures. And as you all know, the 2022 Nobel Prize in Physics has been awarded to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. I have not touched on this because I don't understand this part, but I do understand a little bit of entangled photons and Bell inequality. I'm sorry I had to go through the last few slides a little bit in a hurry. My computer also broke down. So these are the references of beautiful books on quantum mechanics. Each one has his own approach on dealing with the quantum theory. The first one is by Dirac. The second one is by Feynman. The third one is by David Bohm, and the fourth one is by Cohen Tanuji. And this is a famous photograph of Dirac with Feynman and David Bohm with J. Krishnamurti. And he became a philosopher and spiritual guru. And this was translated by my two friends, Susan and Nicole and Dan Strosky. And whatever I have said today is given in my optics book and also in my quantum mechanics book. So for the rest, Albert Einstein in 1917 said that for the rest of my life, I'll reflect on what light is. And then 50 years later, he wrote, 40 years later, all the 50 years of conscious brooding have brought me no close to the answer to the question, what are light quanta? Of course, today, every rascal thinks he knows the answer, but he is deluding himself. So I'm just an old storyteller. I do not know what the truth may be. I tell you the tale as it was said to me. Thanks for your attention. Thank you. I'm sorry I short off my time. So thank you very much.
First of all, it was a wonderful, wonderful lecture. I'm
sorry, I didn't time it properly. The end part was a little hurried for students.
No, it was wonderful, wonderful. So the stage is, so if you kindly permit, so the stage is open for a few questions.
No question. I think these are very simple slides, but the questions will be, you will have to answer the questions.
Professor Ghatak, I have a comment. I strongly think that physics is axiomatic. Quantum physics is axiomatic. So to search for its derivations is in fact rather foolish.
What derivation?
To search for the derivations of quantum mechanics.
To search for a derivation. To search for a derivation. Yes.
It's axiomatic.
It's axiomatic. Yes, you're right.
Yeah. And because it is axiomatic, therefore it can only be disproved by an experiment.
Yes. You're right. You're right.
What do you say, Vengu?
Oh, yeah. You are absolutely right, because I mean, Schrodinger just came up with the wave equation out of thin air. It was just a totally phenomenological response, more than
Yes.
anything based upon fundamental principles.
Yeah.
And
And
speaking about
the story goes, is this right? I have read it somewhere that it was Dubai who gave a lecture, and he said that there must be some kind of a wave equation which must be satisfied by the electron, and then he came up with the Schrodinger equation. I think, is this right? Is this documented somewhere?
Well, I have heard the story, but I don't have a real source for it. So, and the interesting thing is Schrodinger, he was in his 40s when he came up with the Schrodinger equation. He was a relatively unknown physicist who had done some work on color and biophysics before that, but he was not known at all. He just exploded on the scene. And here's a little bit of historical trivia. You said G.N. Lewis gave it the name photon.
Yes.
But the name had been used before. Historically, it was Troland, who was an American astronomer who was looking at luminances and so on. Troland actually used the term photon in a paper in the Journal of Experimental Psychology in 1921.
Really?
Yep.
Oh, I didn't know that. Oh, thank you.
Yep. Right, which is actually because of Troland's work, the level of retinal illuminance is called the Troland.
Oh.
And in fact, I was thinking of writing a historical paper on the naming of the photons.
This is very important, because I have been always attributing it to
G.N. Lewis.
He never got the Nobel Prize, and he was very unhappy, and I think he committed suicide or something like that.
But you see, G.N. Lewis is mainly known for the Lewis-Bronsted theory of acids and bases. He was a physical chemist at Berkeley,
Yes.
and this was named in St. Louis when Compton had a conference on scattering and so forth. But it really goes back to Troland, and there are some indications that even goes back to a Belgian geophysicist who first used it back in, I don't know, 1918 or something. I'll have to hunt up that reference, but Troland I do know for sure.
Excellent. Thank you for giving me this opportunity to speak to such great audience, and I really enjoyed it. And hopefully we'll meet again and talk to you later. Thank you. I'm a little bit in a hurry, Vengu and Akhilesh, because I have to go to Calcutta tomorrow. We are not. I did not remember. So we are still in the midst of packing and things like that. Otherwise, I would love to talk to all of you a little longer and things like that. But thank you.
We will take you up on your offer, and I would recommend all the students to write you letters.
Okay.
Yes.
Yes. I will do that. I will look forward to that. Ciao.
Thank you. Thank you, sir. Thank you.
Thank you so
Have
much.
a safe flight to Kolkata.
Yes. Thank you.
Thank you.
Thank you.
And
Thank you.
you see Professor Hazra there.
Yes.
Okay. I expect Professor Ghatak tomorrow.
Yes.
Okay.
Okay. All right, let me switch this off, recording.